Hi everyone, my name's Dr. Bill Brocklesby. I'm not a GP, I'm an academic at the University of Southampton. And my research work is all to do with lasers, waves of light. But I'm interested in waves for all sorts of reasons, and one of them is surfing. We're going to talk today about the properties of waves. With water waves, those properties are really easy to see. Oh. Those properties are really easy to see. You can see how big a wave is in the water, and you can see how long the distance is between the waves. So you can see the amplitude and you can see the period of the waves. Light waves, it's a bit more difficult, but in this video what we're going to do is talk about how we can find out and how we can measure things like the period and the frequency and the amplitude of light waves as well. Alright, I think that's enough time spent in the water for today because it's getting pretty cold in there. Let's go back to the lab and talk some more about the properties of waves. So here we are down in my research lab. The lasers that we have down in here produce incredibly bright pulses of light. This laser here can produce a pulse of light which is 1,000,000 billion times brighter than the sun on a sunny day. When we were in the sea, the amplitude of the water wave was just how much the surface of the water went up and down. But for light, the amplitude of the wave is how bright it is. This laser over here produces red light, and you can see there's a tiny laser down here that produces green light. And in the case of light, the wavelength of the light is what determines the color. What we're going to do now is head down to one of our lecture theatres where we've been building a model of a wave. And we're going to use that model of a wave to look at the amplitude and to look at the frequency and also to look at the speed at which the wave travels. We're down here in the lecture theatre now, and we're going to show you our beautiful wave machine here. This thing is built up from wooden skewers and these little LED lights you put on the end of your finger sometimes. And we have them all down the lecture theatre, and they're all supported by a piece of duct tape that runs down the middle. So it's a fairly easy thing to set up, but it looks beautiful, and we can use it to show you some of the properties of these waves in a lot more detail. Let me get a wave going down here and you'll be able to see it. There we go. So you can see at once the velocity, the speed at which the wave travels. You can see it bouncing up and down here. When it gets to the end up there, it bounces off. And you can also see very clearly the amplitude of the wave, which is how far the LEDs are displaced from their rest position. And we can make small amplitude waves here. And if this was a light wave, then the amplitude is connected to the brightness. So a small amplitude wave would be a fairly dim light. And we can make big amplitude waves here. And a very large amplitude wave like this would be a bright light. And if we keep the wave going here, you can also start to see the wavelength of the light, which is the distance between the peaks. And we can also get an idea from this of the frequency. Now, the frequency is how many of these peaks travel past us every second. And so if we were to stand and measure how many went past every second, then we would have a measurement of the frequency. There we go. What we're going to do next is just have a little look at some of the maths behind the motion here of the wave. We've seen a real wave on our wave machine. Let's have a look at a picture of that wave. Let's draw some axes. Here we go. So this axis here is going to be our displacement. That's the distance away from the rest position. And then this axis here is going to be distance. So we're going to take a snapshot of the wave at a particular point. So let's draw our wave. There we go. We can see some of the properties of this wave straight away. The displacement maximum is up here. So that's the peak of the wave. And then down here, we've got the trough. And the distance between the rest position here and the peak of the wave, that tells us the amplitude. And in a light wave, the amplitude is the brightness of the wave. You can see the wavelength on this diagram really nicely as well, because if we take a position on the wave there and then go along to the equivalent position on the next wave there, then the distance between those two, this distance here, that tells us the wavelength. And in light, the wavelength tells us the colour. So if we've got short wavelength light, that means it's blue. If long wavelength light, then it's red. So if we had a different wavelength on here, it might look like this. And for that wave there, the distance between two equivalent points is much longer, and so the wavelength is much longer. If we could make this wave move, then we could actually measure the frequency as well, because the frequency is just defined as the number of peaks that go past a certain place in a particular time. So we could measure that, and then if you think about it, if the peaks are this far apart and they pass, that many pass in a second, that means that the speed of the wave is actually the length between two peaks multiplied by how many peaks go past you in a second. So the speed of the wave is just the frequency times the wavelength.